Now we're going to run a hypothesis test for two proportions. So I have here my two populations, actually, population 1 and population 2. And within population 1, I have X1 successes from Bernoulli trials out of N1 total elements in this population. So this population has a size of N1, and out of those N1, X1 were successes for a population proportion P1 of X1 divided by N1. Capital X1 divided by capital N1 means we're talking about the population. In the same way, population 2, the number of successes is capital X2, the size is capital N2, and the population proportion for population 2 is P2. And I'm not trying to estimate or make claims about P1 or N1 separately. What I'm actually trying to make a claim about is the difference between P1 and N1, the subtraction. So the actual population parameter that I'm estimating isn't P1 or P2, but the difference P1 minus P2. So in order to make this estimate or to test these claims, we have to go out and we have to collect a sample. So within the sample, there's going to be a certain number of successes and a certain size. So these N1, lowercase n1, are taken from uppercase n1. It's a smaller set that is trying to represent the entire population. So this sample, we're going to take statistics from this sample to try to estimate the population parameter P1. The point estimate I'm going to use as an estimate of P1 is P1 hat. And the point estimate I'm going to use as an estimate of P2 is P2 hat. But once again, I'm not trying to estimate P1 and P2. What I'm trying to estimate is the difference. So the actual sample statistic that I'm taking here is actually P1 hat minus P2 hat. That's going to be the sampling statistic, or my point estimate. My point estimate is going to be P hat 1 minus P hat 2. And because that's my point estimate, I know that if I take all the possible point estimates and put them into a distribution, I'm going to get this sampling distribution for that point estimate. And let's take a look at the null hypothesis then. The null hypothesis is the hypothesis that the population parameter, which is this difference, P1 minus P2, is equal to some value called the null value. So since I'm trying to estimate P1 minus P2, the value that I'm going to say that equals is D null, which is this D with a subscript of 0. So the null value is D null, and I'm saying that the difference of the two population proportions, I think, is equal to this number, whatever this value is, D null. Because D null is what I'm thinking the actual population proportion difference is, that means my sampling distribution for D null hat is going to be centered at D null. So I know that the center of the sampling distribution of D null hat is D null itself. All right, so basically we're going to try to figure out, when we take our test statistic, which is going to be D null hat, where it falls in the sampling distribution, which is basically the null distribution, since it came from this null hypothesized difference in the two proportions. So this is the null distribution, and we're trying to figure out our sample P hat 1 minus P hat 2, which we're calling D hat null. We're trying to figure out where it lies within this sampling distribution. So we need to know something about the sampling distribution. We need to know its spread, and we need to know its center. It turns out that because we're trying to estimate D null, the center of the sampling distribution is going to be D null. But the standard deviation or standard error for the sampling distribution is going to be given by this formula, which is basically just the square root of the sample proportion, or sorry, the population proportion times its complement divided by that sample size, plus the second population proportion times its complement divided by the second sample size. If you take the square root of all that, you get the standard error for this null distribution. So now that we know what the spread of the null distribution is, and actually we know that because of the fact that if the success failure condition is met, then we know that the test statistic or this null distribution is normal. So as long as the success failure condition is met for both samples, then the sampling distribution that we're calling the null distribution for the difference in the sample proportion is a normal distribution that's centered at the d null, which is the null value, P1 minus P2, and has a variance equal to this thing, which is basically just what's under this radical. So if I wanted to actually calculate my test statistic from this sample statistic, P hat 1 minus P hat 2, I could use a z-score since it's a normal distribution. All I'd have to do is take that sample statistic, P hat 1 minus P hat 2, subtract away from it the null value, which is P1 minus P2, which I call d null, and divide it by the standard error, which is this stuff here. Now, there's a special case. The special case is when d null is equal to 0. If d null is equal to 0, then we get to use something called the pooled proportion, or the pooled population pooled sample proportion. And the pooled sample proportion is simply x1 plus x2 over n1 plus n2, and instead of using the population proportion from population 1 and the population proportion from population 2, we can use this pooled proportion to estimate the standard error. So, to calculate the test statistic in this case, since we're saying that d null is equal to 0, that means the sampling distribution is centered at 0. So all the sample differences will be centered around 0. And the standard error is calculated using the pooled proportion this way. So it's going to be a normal distribution with 0 as its mean and this as its variance, which is basically what's under the radical here. So we can calculate a z-test statistic in this case, which is just z equals the sample statistic, P hat 1 minus P hat 2, minus the null value, which in this case is 0, divided by the standard error. Okay. So here we have an example. In a recent Gallup poll, 992 Americans were asked about their views on abortion. Of the 561 men surveyed, 30% said they are in favor of abortion being legal under any circumstances. Of the 431 women surveyed, 38% said they were in favor of abortion being legal under any circumstances. At a 5% significance level, test the claim that the proportion of men that are in favor of abortion under any circumstances is less than the proportion of women that are in favor of abortion under any circumstances. So I see here that I'm trying to test the claim that one proportion for men is less than the same proportion for women. So that means I'm going to take a sample of men and sample of women, and within this sample of men, there were 561 men, 30% of those said they were in favor, and of the women, which were there were 431 in the sample, 38% said they were in favor. And what I'm trying to do is I'm trying to estimate P hat 1 or P1 minus P2 with P hat 1 minus P hat 2. So this is my point estimate for P1 minus P2. But because I'm trying to test the hypothesis that it's either equal to 0 or that P1 minus P2, since I think that the men have a smaller proportion that are in favor than the women, I would say that my alternative would be that P1, the proportion of men, is less than the proportion of women, so that if I subtract, I should get a negative number less than 0. So since the proportion of men I expect to be less than the proportion of women, this difference I expect to be negative or less than 0. And that's where this null and alternative hypothesis come from. So the null hypothesis is that they're the same, that men and women feel the same way about abortion under any circumstances. The alternative is that the proportion for men is smaller than the proportion for women, P2, so that when I subtract them, I should get a number that's less than 0, a negative number. And because it's a less than, I know that this is going to be a left tail test, and I'll be able to find the p-value as the area to the left of my sample statistic. So I'm going to go ahead and calculate a test statistic so that I can find that p-value as the area to the left of a z-score as opposed to an area to the left of a sample statistic. So I know that it's a normal distribution with a mean of 0, and this is the variance, and I'm using this pooled proportion. So this is how I'm going to calculate the z-score. It's going to be p hat 1 minus p hat 2 minus 0, which is what I think the center of the null distribution is, all divided by the standard error. So I get these numbers. P hat 1 is the 30% of men. P hat 2 is the 38% of women. P bar is calculated as 30% of the 561 men plus 38% of the 561 women, which is x1 and x1 and x2 respectively, divided by n1, which is the sample size for men, plus n2, which is the sample size for women. When you do this, basically x1 plus x2 over n1 plus n2, you get this number, 0.34625, which is why I'm using that as the pooled proportion within this standard error formula. So this will give me my z-score, the value minus the mean, which is 0, divided by the standard error. So that z-score is negative 2.625 when you calculate it. And that is my test statistic. Now, with this test statistic, remember, the z-score is the area to the left of the sample statistic, which is identical to the area of the to the left of the test statistic that corresponds to that sample statistic. So this is the test statistic that corresponds to that sample statistic. So if I find the area to the left of this p-value, if I find the area to the left of this z-score, that will be the p-value. So in order to do that, I'm going to use Python. This is the code that I would type into Python. I'd import scipy.stats as stats, and then I'd do the stats.norm.cdf, which gives me the area to the left of anything I plug in. And what I'm going to plug in is that test statistic I just found, negative 2.625. And when I plug that in, I get this, and this is what I run. When I run Python, I get this. So that's my p-value. That's my p-value. Now, once you have the p-value, you can then make your initial conclusion. If the p-value is less than or equal to alpha, that means that the sample we observed is more extreme than the cutoff point that we call the significance level. The significance level was 5%, and I found that mine was less than even 1%. It was about 0.4%. So my cutoff point for something significant was something that was 5% or less. And I got something that was way less than 5%. This means that the null hypothesis is probably false, or we witness a sample that was a miracle. So because my p-value is less than my significance cutoff, I'm going to reject the null hypothesis because we know we don't believe in miracles in statistics. So this distribution was a miracle, because if the null hypothesis is true and the actual average is 0 and the actual center is 0, what we just observed in our sample was so far away that it won't only have a probability of 0.4% of happening. So we know if something only have a 4 in every 1,000 chance of happening, that's extremely unlikely or a miracle. So we're going to reject that distribution. That null distribution is probably false, which means the null hypothesis is probably false. So I reject the null hypothesis.